Thank you very much.
Thank you.
Just let me share my screen. First, let me introduce myself. I'm Nikolaos Triantafyllis. Nikolaos, it's the full name. I'm a software engineer. So my specialty and my field is computer science. But somehow I was engaged to also seismological stuff too. So I'm a software engineer in HPC, high performance computing. Perhaps some people have heard of that. HPC or supercomputers, cloud computing, it's known terms. And I'm working on my PhD is on HPC enhancements and making the software better in terms of algorithms. However, in the past, mostly I was working on computer software on seismological suites, starting from ISOLA, which was my master thesis software implementation. Now, as ISOLA has been abandoned and Gisola has took its place, which is a more it's a newer software with much more features and enhancements. Gisola was a part of a project that has been funded for automating the moment tensor computations. The name itself, it shows that the core component of it's Gisola. So someone who wants to use Gisola should and must have a prior knowledge on how to use Gisola. The G comes from the multi-nodes, multi-core systems. It's from GPU, which is on we accelerate computations. So can someone have a quicker outcome of their result? So let me start with Gisola, which is a real-time moment tensor computation software. Most of it's written in Python. Of course, it's open source, so anyone could use it freely, and anyone could contribute to it, fork the repository, and implement their own features, modules, whatever. So it's an open source and free software. It's mostly Python based. However, since it's Gisola related, some core components like the inversion code and the green functions computation is written in Fortran. And some also code, since it has a graphical user interface through web facilities, it's written in web computer languages like HTML and that kind of stuff. So this software, what it tries to do is to automate the moment tensor calculation, and it tries to combine it with web services that are online through different agencies. So can someone do the entire procedure as automatically as possible and without, let's say, losing their time on how to prepare the data and that kind of stuff. Now, why use Gisola? Why not to use Gisola? If someone wants to do manual stuff and wants to prepare specific events, specific kind of information, they should go for Gisola. Gisola is mostly for, let's say, three main purposes. One is for real-time event monitoring and MT calculation. So it's probably targeted to civil agencies, let's say, or observatories and agencies that are responsible for notifying people about earthquakes and the outcome of the earthquakes. The other way is to use it as a batch, let's say, MT calculation. So you want to perform a mass of MT computations for a particular region or a time domain. So it's very useful in that kind of stuff. And also, if you want to perform a very, very dense computations, for example, you want to have a very dense grid of source points, and you want to, let's say, for research purposes, you want to have a very dense computations which take a lot of time, also for the computation part, and also for preparing the input, let's say, to the program. I attach here the GitHub repository where you can go and download the code and use it. And I will start with some operations that it's being used right now. So the major agency for Greece is the National Observatory of Athens, specifically the Institute of Geodynamics. If you visit the webpage, you could see that it runs there the MT computation in real time. Actually, in fact, I'm going to skip here and show a little bit from the webpage. Okay, so this is the webpage from National Observatory of Athens, and this is the particularly the page of moment tensors. In fact, while we were having this webinar, there was a small earthquake happening in Philippiada area in Greece. And as you can see, the software automatically calculated the MT computation. You see here the A. I'm not sure if can you see this from the share of screen. I'm going to click on the information. As you can see, the evaluation status is preliminary. So, and also the evaluation mode is automatic. So it's something that processed automatically without, let's say, the hand of a manual operator. And this is the event. We can move later on what we see here, but I just wanted to mention it because this event just happened a few minutes ago. The hour here is in GMT, so you have to calculate, let's say, to figure out your based on your time zone. So now moving to the slides. So one agency that uses Gisola is the National Observatory of Athens. Another use case is in the Albania, the Institute of Geosciences, that they also use Gisola for real-time operations. And also we see that the Universitas Negeri Surabaya, UNESA in Indonesia, also they operate in real time the moment tensor computation extracted from the Gisola software. I'm going to give some, let's say, process of a flowchart of the process that is going through the whole procedure of an MT, let's say, computation. So basically, the first thing that we do, that Gisola does, is to check for new events. To do this, it is okay. Gisola has a configuration file only, so it uses only one configuration file, and everything is there. So you have to prepare a configuration that it is good for what you want to do.
If you want, so if you are an agency and you want to have real-time momentary computations, then you have to specify how you retrieve these events. So currently it supports the FDSN, which is a very FDSN-WS, which is a very well-known standard in seismological society. And particularly it uses the FDSN-WS event to retrieve seismic event informations. Then it can filter events based on specific characterizations like magnitude or some qualities of the origins or geographical restrictions that you want to have. And the reason for that is you might want to wait to have a better estimation of the origin. So these quality indicators shows you that wait, do not start the computation yet. Perhaps it's going to be, let's say, a second round of a better estimation of the hypocenter. These features here provides this opportunity to have, let's say, a better MT computations, because if you put garbage in your input, it's going to be garbage in your output. So you have to be very careful of what you give to the program. Then the second phase is to select the inventory, as it's well known. There are various options to retrieve this kind of information. Again, the most popular is the FDSN-WS station. But also you can provide a station XML file format with your inventory as you like. Then again, it filters stations based on specific information, like the priority, which it is a manual way. No, it's let's say it's a way that someone could give prior knowledge to Gisola on how good or bad stations are. And then we select the inventory based on distance rules. We will see later how these distance rules work. After selecting the stations that we're going to process, then we go for the waveforms data. So we use mostly the seedlink service, which is a real-time waveform retrieval protocol. But also you can use FDSN-WS data select. Most services usually have archived data there, not real-time, but some of them have also real-time. Or you can use an SDS structure, which is a Syscom proposed MSEED format archival method, let's say, protocol. Then after retrieving this waveform, it filters them based on specific modules that are implemented. Currently, we support a clipping module that finds waveforms that they are clipped, a signal to noise also module. So if you have a very high SNR, it automatically removes the waveforms from the computation. And we have also a mouse called disturbances. This is described in papers with in papers of Professor Sokos about that. And also another module that is implemented is the power spectral densities, which provides another type of information on how if the waveforms are good or bad for the rest of the computations. Of course, there is a space there, so anyone could implement their own modules. So we are happy to see people working on new modules and integrate them inside Gisola. It's actually easy to do this. And then after this filtering, we remove the instrument response, and we do this in a parallel CPU processing. And then, okay, then we implement some methodology on how we select stations, which is, I would say that in Gisola is one of the most difficult things that does. So it selects stations based on azimuthal coverage and priority of stations. Then it computes the green functions. This is a part that we, for technical reasons, we do this every time that we want to calculate moment tensions. But this is a part that it could go to a predefined phase. So you have to provide some information how you want. Okay, Gisola, what does it creates a 3D source point area, and then it calculates for each point the moment tension. So you have to specify how the grid is of your computations. Of course, if you have a very sparse grid, you will have quicker results, but the solution might be not very good. If you have a very dense grid, you will have probably a better solution, but also you'll have a lot of time spent in computation. So you have to find a golden, let's say, thing to solve this, to have a good configuration. After the green functions computation, you will have the compute of the inversion procedure. This is a 4D spatiotemporal grid because you also Gisola also computes the inversion on time, so it shifts in time points and calculates the moment tensors. For this purpose, the computation has been designed both in CPU parallel processing or GPU. So it depends on your hardware facilities what to use. And then after the computations, it's the distribution of the results. There is an HTML web page as the one you saw before in the National Observatory of Athens, which is rendered. You can also, since the event it's exported in a QuakeML format, which is a very well-known format for describing events in seismological society. You can publish the results whenever, in the way you like. There is an email notification system. This is mostly for real-time operations, if you want to get notified after the computation. But also you can apply user-defined scripts, like, for example, you can ingest the empty solution back to a syscomp that already runs operations there. So you can enhance the event with moment tensor information. But mostly the two last points, it's for real-time operations, and it refers to civil agents, probably. I would say that you could visit the wiki in the Gisola GitHub page. There is an extensive explanation of the entire documentation on how the methodology is, how you can install the software, and how you can configure the software. Configuration is one of the most important stuff there. And then there are examples of the usage of Gisola in real-time operations, but also for let's say in batch operations, if you want to process a lot of events all in once. And also a description of the available modules and how they are working. Again, to remind you that the modules is a part that filters waveforms. So these modules are responsible to, let's say, choose and select the appropriate waveforms for the operations. And then we will move to the configuration part. So I'm going to pass through a typical configuration file, which is in a YAML format that the user or agency pass to the Gisola software. So if you are interested for real-time seismicity, then you have to specify information here. If you are not, you can skip this information because this is for real-time retrieval. The first thing that you have to specify is the service that provides seismological information through the FDSN WS event web service. So, for example, in Greece, this is the main website where you can download FDSN WS event information, and as we will see later, also station and waveform, inventory and waveform information. Here you give some information about the quality of the hypocenter and the magnitude that is related to the hypocenter origin that you want to have in order to trigger the inversion. The reason is doing that, as I mentioned before, is because you might want to wait for a good, let's say, hypocenter solution, and it might take some time and some, let's say, operation cycles to have that available. But also you might want not to run events in cases that, for example, you see a very bad origin estimation. Then there is a mechanism on how you can let it, okay, this is more technical stuff. Gisola can give you the ability to run, let's say, to run it in a historic, to have a historic run. So you can play back events in Gisola and see how this operates. This is very useful if you're an agency and you want to find, let's say, the time thresholds on when to check for new events, etc. And also the GeoBox provides the area where the MT computations are going to be that indicates the bounds of the computations that are going to be performed. And then we are going to the selection of the inventory. So this part here, as I mentioned before, it supports various types. A typical type is the station XML, so you can provide your inventory in XML format, which you can easily download or create with various tools, and you can also download through FDSN web services directly. Apart from that, you can also specify an agency that provides FDSN web service format information. And what it does here is to process multiple sources of input one by one, and let's say it aggregates the information, and in case of duplicates, it keeps only the one, the first occurrence of let's say station data. And then there is this information provides let's say it gives some priority to the stations that we are interested on computations. For example, someone could say that this network, it's not very reliable. I want to set a priority to 0 because I do not want to retrieve, I do not want to involve this particular network to operations regarding MT computations, for example. There is an extensive explanation on how to create this kind of files in the wiki page. And then we have the first, sorry. The first part of rules that indicates what kind of priority we should take into account. For instance, this line here says that if I have an earthquake from 4.6 to 5,
use priority number 3 of stations. So if you have stations that are priority of 1 or 2, these are not going to be used in the inversion. Next phase, again in the inventory selection, is to provide the components that are going to be used, which mostly this is well defined, and usually you do not need to do anything about that. But the most important here is to specify good rules concerning the distance here. This rule, for example, okay, now assume that we have an event of magnitude 5.8. So Gisola will trigger these two lines because 5.8, it's between 5.6 and 6. So it will trigger these two rules. And it says that select BH or HH channels of waveform data that are between 50 to 450 kilometers from the epicenter, and similar to the rest of it. So these rules are working in aggregated, so it will take what it can based on the condition here and what it can based on the condition here, and move these stations for the next phase. So the next phase is similar to the inventory, but now we will retrieve waveform data. Usually, if you want real-time operation, you will specify signaling as the protocol to use. If you are not interested in real-time operations, for example, if you want batch computations, you can use SDS structure, which is data that you have locally in your drive in a SDS format. There are tools to let's say, convert your data to SDS format structure. Otherwise, you can use directly FDSN web services that uses the data select and retrieves the waveforms, and Gisola can do that for you. Again, this works aggregatedly. That means it will try to retrieve data from the first web page, from the first web service, and then from the second web service, and etc. One of the most important parts here is the modules that are going to be used in order to filter the data. So you can have, for instance, clipping detection system or SNR detection system, or you can have mouse detection system. And one that it's missing from here, but it is available, is the power spectral density information. These are described very well in the wiki page in the module subsection. Particularly the power spectral densities has two operations. There is one which is the offline and one which is the online. The offline, it gathers information for the power spectral densities of seismic stations in offline mode, I mean, not in real time, while the online mode, it performs the operations on the fly. This also means that it takes more time for the computation. So as you can see, in many cases, there are a trade-off between computation time and actions like more computations and more, let's say, sophisticated algorithms in selecting data. Okay, so the next phase is to select waveforms. Actually, when we retrieve the waveforms from the previous step and filter them, then we select waveforms based on the azimuthal coverage that it has been configured. What it means here is that let's say we have a hypocenter at this point here. We have an 8-sector circle, which is each sector is 45 degrees, and we tell to the configuration, for example, here, that we want to have we want to have stations from 3 sectors at least. And the second number says that from each sector you will have at most 2 stations. Why do we have this? It's because we want to have a good distribution of data. Because a good distribution of data will manage to have a better MT solution. Now, why we have the second number? We don't want to dominate the solution based on particular sector. We want to have as much as more distributed and equal data. Then we have the green functions computation. So again, you describe here based on the same pattern. So you have the rule of the magnitude. So if you have an earthquake, let's say of 5.8, you will this rule will be triggered only. Of course, you can have multiple rules, so you can trigger multiple grids. This means, however, more computations. So you have to be very careful about that. And moving to that particular rule, what it says here, it constructs a 3-degree of source points that it's going to calculate the MT computations. And our grid here, it's not homogenized. It means the spaces between steps, it's not the same to all cases. So, for instance, we create here a grid which starts from 0, where is the hypocenter, let's say, to 9 kilometers with a step of 4 kilometers. So, for example, here we have 0, 4, 8. So we have 3 points in the x-axis. Again, and then it creates another, let's say, subgrid that starts from the 15 to 21 kilometers with a step of 5. Similar to the distance, it's the depth. So we create here a 3D spatial grid to indicate where we want to run our MT computations. Then we have to define the crustal model. As we mentioned before, Gisola is related to ISOLA, so it uses same methodologies and information there. So we have to specify here the crustal model that we are going to use. So you have to provide your crustal model on your specific area, and then you can specify particularly which geographic location this crustal model concerns. So you can have multiple cases. If you are not aware what to use, you can put null here, so it's going to take it and use it anyway. As mentioned before, Gisola works in an aggregated manner. So if you specify, if your hypocenter can, let's say, fulfill this condition of the first geobox and also from the second geobox, Gisola will run 2 different computations, one using the crustal model, let's say, of Trakatos here, and the other one of Haselinger. So it will create 2 different, let's say, aspects of the MT solution, and will choose the one with the best variance reduction. Again, this is you will pay in cost of time, right? So you have to choose very carefully. Then we have the inversion. So in a similar manner, we have which kind of okay, the time shift here indicates, let's say, similar to the 3D grid. Now here indicates the time shifting of the computations. while the window here, it's indicates how many seconds of data are going to be inversed in the procedure. So assuming we have an event of 6.2 magnitude, the third line of the time shift will be triggered, which indicates which particular time shifts it's going to be performed. And also it will take a time window of 409.6 seconds in order to invert those information. And the third stuff similar is the frequency that is going to be used for the inversion. As you can see here, two lines were triggered because they are on the same magnitude range. That means that Gisola will compute two times, let's say, it will have two different types of computations, one with this frequencies, and the other one with the other frequency band. So again, it will choose the one with the best variance reduction. But again, you will it's a trade-off between time and good quality solution. One thing that it's not implemented that ISOLA has is that it's going to use the entire it will use the same frequency band for all stations that are going to be chosen. So you cannot specify currently different frequency band for different stations. There is a trick that you can do this manually by changing a particular file after the first time the inversion runs, and then you can rerun, let's say, the inversion, but it's not suggested. However, we would like to see people, if they would like to contribute to that and implement Gisola code to have this feature. And this is about the inversion computations. What we see here, as we said before, we have a 4D spatiotemporal moment tensor grid search. So what we see here is there are three cross sections. So we have, let's say, a cube. Imagine a cube, and we cut it in three ways. One is from top, so we see the solution from top of it, and the others are we use south to north and east to west vertical cross section, and the moment tensor in red. I don't know if you can see that. It's the most correlated solution there. There is also a time depth here. I want to mention that this 3D grid search that it is shown here, this 3D grid view, it provides only the best correlated time search of moment tensors for its grid. Now, for the best of it, here you can see a time depth information here. So in the x-axis, it's the time shifts, and the y-axis, it's the depth of the best solution. So this is a preview of the overview of the map view, and then you can distribute the results. There are there are more let's say HTML web page information there. When this happened, what are the major information that we need to know, show us in map where exactly and what is the focal mechanism, also the quality, which is explained in our papers, how this is measured here. You can have a mail notification or send the solution back to Syscom. This is an overview of the HTML page that you can use. You can use even as a user. I mean, you don't have to be an agency for that to view your solutions there. This is an overview of the MT computation for a particular event. It provides us here the basic information of the event, some IDs, types, the quality metrics of our solution here. If you remember the ST bar and FM bar that was mentioned previously by Professor Sokos, and also other quality metrics indicators here. You see information about the hypocenter that was used for the computation. Remember that garbage in, garbage out, so you have to be, if the hypocenter is located, for example, in a wrong place, you will have a bad solution, right? And then you have the centroid origin here, information. They used stations, how much stations were used, what's the azimuthal gap. The stations are sorted from min to max distance from the hypocenter, and also a map overview of the solution. There is a waveform analysis that shows, similar to ISOLA, observed synthetic waveforms. And also you can view the waveforms as it were extracted from the FDSN services. If you see, you can see here that some are unused. These were automatically filtered by the modules based on specified thresholds that were chosen. You can change that your configuration, not in the configuration file, inside the modules if you want to have a particular different threshold for some reason, or you can deactivate particular modules in your configuration. Again, here is what I told you before about the cross-section plots. Also, it shows the best MT solution based on the variance reduction. And you can see here an example of the QuakeML format, XML format of the solution that it's provided, which now ingests the MT and associates the origin, the events, the event, it's associated with the moment tensor. Also, it provides in a text-like format. Of course, there are some share buttons to use it in X Twitter or email notification of your result. You can dispatch the empty solution back to Syscomp. You can use your, like a web page, you can use your mobile or tablet to view the results. And let's see here some, I don't know if we have some time. Some applications that can be used. You can use the FDSN WS from regional areas. So if you know the specific node, like the Greek FDSN web service, or let's say the Italian web service, etc., you can use it as itself. You can use the European area by using the ADA federator, which it's like a front end of the rest of the web services, but it takes longer time. So depends on what you want. You can have a worldwide like computation by using or the European FDSN web services or the Irish FDSN web services. Again, you can have different kind of applications and give a specific configuration file in each case. You can also have run multiple Gisola, let's say, instances with particular configurations. For example, if you want to just to indicate the moment magnitude, the MW, then you can have, let's say, a more sparse 4D spatial temporal grid search. So you can have, let's say, quicker estimation for edged warnings. If you want a typical real-time application, then the configuration that is indicated in the wiki page it's let's say a normal case study.
And if you want something for, let's say, your research area, so it's research applicable here, you can have, let's say, very best quality MT computation using a very dense for the spatio-temporal grid search, using a lot of frequencies bands, using a lot of different grid searches. So you can have multiple computations and let then Gisola choose the best correlation to that. Okay, you can use, as I said before, you can use a configuration and in different instances, so you can monitor different FDSN web services for events. And again, you can restrict events based on specific quality data. We can see here an example of how someone can use it. So a typical use is to provide the executable, give an event based on the FDSN event ID system. So you have to know what's the event ID and the configuration file that you provide here. It must be complying with the FDSN web service event there. That means that this event ID must exist in the FDSN WS event. You can also provide multiple events, like here we put here 2 events, so you have two empty computations with one run. Of course, there are other ways of computing. This probably will be more interesting to you. Again, you have to specify a configuration file, set the FDSN web services that you want. If you do not pass here the configuration file by default, it's going to take the local file config.yaml. And the most interesting part here is that you can give this input to Gisola, which is a daytime range starting with a starting point and end point. So it will try to calculate all the events found in this daytime range that are can be extracted from the FDSN web service event, and also all the rules that they are associating the configuration file are matching the size of the magnitudes. For instance, just a second. Here, if as you can see here, we cannot calculate events that are less than 3.4 or let's say 9.1 because these rules here indicate the magnitude range. So if are not specified the magnitude range that we are interested in, the daytime range won't make any sense because it will pass through the conditions. There are other ways too. You can provide the information in a more, let's say, text-wise, text-like format. You can also provide some information like, I want to use these particular stations, and actually from the last one, I do not want to use the Z component. You can specify which particular crustal model to use. Another interesting thing is that you can have only the revision procedure. So if you run the computation once and you just want to specify different frequency band, you do not have necessarily to run Gisola again from the beginning. You can provide the minus revise to start from the inversion phase, skip all the other phases like green function computation or retrieving data again, because these data are already there, and do the inversion and the plotting of the results. Again, here is for real-time operations. You can have cron jobs if you are familiar with Linux wise configurations, let's say, where you can have a monitoring type of operations here. And okay, we have a future step to that. We would like to have green functions pre-computed, so we have quicker computations. We are interested in neural networks and deep learning and machine learning event-driven approaches. Also improved mechanisms in characterizing the waveforms quality, like the modules I was mentioned before. And here you can find the source code. This is the wiki page, which is an extensive documentation here. There is a discussion page where you can ask your questions, you can suggest improvements, etc. here. So you can open a discussion topic there with if you have any problem there. Also, we would love to have you contribute to Gisola. You can contribute in various ways. You can share your data, for instance, crustal models of your area. You can share, if you are more, let's say, software geek, you can share, let's say, new HTML-like templates, or create your own new modules that, for example, they are ML aware of bad, let's say, signal detections. You can share also your configurations, because configurations are very important, because all this information like distances, inversion, time that is going to be chosen, and that kind of stuff are related to the network distributions and the networks that are provided in the area that you are interested in. So you can have regional empty computations. This is Gisola 4. But if you have a lot of FDS web services and a lot of configurations, you can have, let's say, regional moment tensor, but from various areas. You can read more here in these two publications concerning the Gisola. I will also share the slides with Diane, so you can distribute it among the rest of the people here. And I would like to thank you for this opportunity.
Okay. Thank you, Nikos, for the interesting presentation. Now we will have maybe a shorter time for the Q&A before the open discussion. I would like to we have one person raising hand. Taufik Rafi, could you deliver your question? Taufik. Taufik, could you please? Okay, maybe I would like to ask some question, Nikos. From your presentation, it is shown that Gisola is really comprehensive. You can have many frequency band, time window, and time shift options. But I would like to ask about the inversion method. Does the Gisola also covers the full waveform inversion, or deviatoric, or the DC only?
Currently, it's deviatoric. And am I correct, Prof. Efthimios?
Yes. It's only deviatoric now.
Deviatoric, yes. So yes, you can only use this right now. We haven't tested. Theoretically, you could test other methods, because if you modify some particular ISOLA files, then Gisola it's unaware of that and will perform the rest of the computation. But we have not tested that, so we cannot suggest it right now. But you're free to test it and also let us know about it.
Okay, thank you for the answers. Okay, do we have other Adek, you can deliver your question.
Yeah, thank you, Miss Dian. So I want to ask you, Mr. Nikos, if we have a local data archive in our computer, can we run also the Gisola from our local disk archive? And we have many event also and doing multiple running, like you said before, like a configuration with batch many file, many events in one time running from local archive. Can we do that?
We lost Nikos, maybe.
Yeah.
As far as I know, yes, this is possible. So I can reply for Nikos.
Yeah, sorry, my apologies. I had the problem with Zoom.
Okay, so
Yes, you can use your local archive. Actually, if let me also share again, please. Okay, if you go at this wiki page, you will see at the installation, sorry. There is a way that you actually, when you compile the code, you run a test, like a sanity check functionality, a test that shows that you successfully installed Gisola. So here you can see that you provide this configuration file. I will show you what, and here you also have the event locally in your disk. So if we go now to this folder, this is the test. You can see here, I don't know, can you see? Is it
yes.
okay? So we tell here that we are going to use a station XML file format for collecting the inventory information. So you can provide the inventory information locally. You can also provide here an FDSN event information. So if you provide it through FDSN, then it will try to retrieve this information through the web. Similar to the inventory, it's the stream also. You can have your local data in SDS format in your local archive here, as you can see. So the test case, it actually does not use any web service at all. All the data are here. So for instance, we can also have this run as we are talking. So let's do this. What you have to is to activate the framework, and something that it's very important is to use this particular command. You can also have that permanent, so you don't have to do this all the time. And we will give to Gisola this example. So we tell Gisola to run it based on this particular configuration file, and we want this particular event, which is described in a quick ML format. Now we start the computation. This runs locally on my machine. As you can see, this event information is retrieved from the XML format. This inventory is retrieved from the station here. Okay, from the inventory XML here. These streams are provided by the SDS archive format. So here you can see an SDS-like archival. So if we go in the benchmarks archive, it's in a format. This is the networks, the stations, the channels, and the minisite files, the daily minisite files. Actually, if you Google SDS, it's a particular format.
Let's copy the data structure, right? Okay.
Yes, exactly. So you can provide your data in that way. There is also a tool, it's called FDSN to SDS, so you can use an FDN service to download the data in your SDS structure. However, I mean, this is necessary because you can provide the FDSN web service itself here, so you don't have to do this step unless you have a reason to do that. You will also provide the crustal models and the rest of the information. And as you can see here, this is the clipping, the modules that were used. For example, a clipping check was done. This was passed. This was failed because it didn't reach the threshold. Then there is a chosen of the azimuthal coverage, as we mentioned before. So these streams were selected that were qualified for the rest of the application. And then we have the grid selection and the grid computation here. And after that, we start having the inversions. You can also see the moment tensor computed for each batch of 100 source points. But ISOLA will calculate all of them and will choose the best correlated. So we are still performing computations. Yes, so I hope I answered your question. So you can use local station and stream data. You can follow the example of the one indicated in the wiki. So it's easy to follow the same format.
Okay, thank you, Mr. Sokos. Maybe for the next question from another participant.
Thank you, Nikos and Prof. Sokos. Maybe we should we still have two questions. The first one is from Taufik, asking about stress inversion. Does the Gisola has a plugin about the stress inversion, and how about the segmentation?
I think Professor Sokos could answer on that.
Yeah, this is not a code by Nikos, right? This is a code by another student, which is okay. It is using a lot of Gisola. And no, you cannot define by hand, let's say, the polygon areas. You just upload the file that has the coordinates of the zones, of seismic zones. This is the first question, I guess. And the second question I was just reading.
Yes, the second question is from Yaskiel. He's from BMKG, the Indonesian Earthquake Observatory Agency. Maybe I could read for the last question. There are one question and one suggestion question. In my opinion, one of the important aspects of automatic analysis is the selection of the best quality data from each sector. I see there are several approaches such as mouse, SNR, and clip. My question is there any weighting scheme in your inversion formulation based on the data quality? Because from the approaches, he feels that one of the most robust is mouse, which can detect data disturbance that sometimes result in high SNR but not an earthquake. However, sometimes they escape detection and their significant amplitude greatly affect the solution. How do you handle this?
Yeah, there's no weighting scheme for based on the data quality. The modules that check for, let's say, problems in data are on off. So if they detect a problem, they will remove the component or the station. I don't know if this answers the question. Nikos, you want to comment?
And I have nothing to comment, sorry.
Okay. And the other question is about the frequency band. I do not agree very much with this because, you have an instrument that, of course, has a lower frequency of 100 seconds. Okay, this is the typical broadband instruments, but it does not mean that your signal is free of noise up to this frequency. It depends on the installation of the instrument also. So if you don't have an instrument that it is on bedrock or it's buried, it is not affected by atmosphere changes, by temperature changes, then okay, you can say that you can record so long periods. But if you have a surface installation, then you probably have noise in long periods, even with such a good sensor. So it's not only the sensor corner frequency that explicitly will define the lower frequency that you are going to use. It depends on the noise of your site. So it is, of course, sensor plus installation. If the site is not well constructed, if there is no good thermal protection of the sensor, then you will have noise.
Okay. Thank you, Prof. Sokos, for the answers. And also thank you, Nikos, for the great presentation. Maybe to save time, we will move on to the open discussion for the possible collaboration of the possible collaboration. I would
Yes,
like to.
sorry, just to show a little bit, I just ran the test event here. So
Okay.
there is then you can view the results here. So you see this event, you see the informations, which stations were used, the data, the observed versus synthetic waveforms, displacement data in meters, and also the best solution that correlates to the 4D grid search. So I strongly suggest that you everyone who wants to run Gisola first run the test event and should have a solution like that. I'll stop my screen.
Okay.
Thank you.
Okay. Thank you, Nikos. Maybe I will pass it to Dr. David for the next talk for the possible discussion, possible collaboration. Thank you.
Okay. So thank you, Dian. Thank you, Nikos, for the very interesting presentation, and also thank you, Professor Sokos, for the interesting presentation. I think I hope that a lot of students are joining our this workshop, and hopefully they learn a lot, and they can we can together perform a kind of a joint research of moment tensor inversion in some area, especially in some area in Indonesia.